unrelentless. You are terrible. Okay, last lesson we talked about the logistics curve, and the logistics curve is this particular kind of differential equation where the population change of a particular thing is kind of like balanced out by these limitations. So we talked about how, like, for example, there's limited food or there's limited prey. The other one that I thought about was viruses. When they spread in a body, there's only like limited cells that like you can actually like the virus can infect, right? And so at the beginning, it's going to infect a lot of cells, but then over time, the like number of cells that it can like infect is going to like taper off because there's not any more cells to like infect. So that's what this kind of equation is used for, and it's also used in like populations as well. So like we're in for like coronavirus. You get like if we just like went around and like just did everything normally, it'd be like fairly exponential at the beginning, but eventually after a while, when there's like less people that are like uninfected, it starts to like taper off, and the growth of like the number of people who are infected like tapers off like that. And so what we did last lesson was we went through a couple of questions. Well, we went through this first question of actually how we answer these particular types of questions. And what we actually did, there's a few steps, and this is just like a quick summary that it's not on the booklet, but like just in general, when you get these questions, and it's similar to exponential growth and decay questions, there's kind of like a few styles of questions that you're going to notice. So types of questions with exponential, so this is exponential growth and decay, and also this logistics curve type of question. So the types of questions that you're going to get, and let me just check that this is correct with my notes that I have here. Yes, this is correct. Okay, the types of questions that you're going to get. Firstly, there's going to be questions where you want to show dp on dt is equal to kp or kn p minus n. Or some variant of this. Hang on, let me just get this right. I don't think it's right. It's the other way around. Whoops, might be kp n minus p. And so what we have to do here is differentiate and rearrange original equation. So this was that first example that we did at the end of in last lesson. We actually went through and differentiated, and also then we rearranged the original equation so that we can sub it back in and we get it in this form. The other one is when we have to sub t is equal to 0, and this is like when it says, like, if it says the words show at the starting time, or like the words originally. If we see those keywords, that means we need to sub t is equal to 0. The third one is we want to see, this is particularly for the logistics curve kind of questions. If they ever say the words eventually, or what's the other thing? Eventually, or what was this one? Yeah, eventual. Do you remember what we had to do if we want to find out if it ever says the word eventually? What do we have to do? It had to do with time.
T equal infinity.
T goes to infinity, yeah. So we take the limit. And usually, what that would do is, when we sub that t goes to infinity into our exponential, it makes the exponential become 0, and then we can like work backwards, and then we can get like a value for the population that happened. What will happen to that population after like infinity. And the fourth one is like the other questions, and this is just, we have to like read the question carefully, read Q carefully, and do what is required. So the first three are like fairly standard questions, and I've highlighted this yellow one because it just only applies to differential equations. But what we want to do is, often we want to differentiate, rearrange, and then put our thing back in. And then the other bits is like sub in t is equal to 0, sub in t is equal to infinity, and then there's some other questions where we need to like rearrange and do stuff differently. I'll give you a second just to write that, and I'll check up on Boyd.
Okay.
Any update?
Right, so technically this lesson is like, it's not allowed to be made because it's
Shh,
only me and
can't stop
okay.
talking. Can't stop talking.
Okay.
Shh, shh, shh. Bleh.
Okay.
We didn't say anything. The video. My PC currently is showing video. Okay. When you're ready, let me know, and then we'll turn over the page and we'll have a go at the question over the page.
Okay.
Okay, so let's have a look at the question over the page. Here, this is from an extension 2 paper. Now, even though it says extension 2, this was this is a question from this extension 2, but now because of the new advanced course, they've actually kind of put these styles of this is like a logistics curve question that is now in the extension 1 course, unfortunately. So, let's have a look. The population P of elephants in the Serengeti National Park is given by this following equation. So here, we've got this equation that tells me the populations of elephants, where T is time in years from today. Okay, part I. Show that the population, so show that P satisfies the differential equation dP on dt is equal to 1 over 3, 1 minus P over 3,000 times P. Okay, how might I start doing this question?
Differentiate.
Now, before we do that, what I recommend you do is just rewrite this equation, but with index form, so that it's easier to just apply the chain rule. So what is this in index form?
So P equals 21,000
Yep.
times 7 plus 3 e to the power negative t over 3 to the power negative 1.
Excellent. And so we can start to differentiate this using our, using our chain rule. Okay, so here, dp, oh my gosh. And my computer's lagging. Okay, dp on dt is equal to, what am I going to get when I differentiate this?
Negative 21,000.
Negative 21,000.
Times 3e. Wait, no. Negative e to the power.
E.
To the power of negative t over 3.
Yeah, excellent. So here you differentiate the inside function times
7 plus 3e to the power negative t over 3 to the power of negative 2.
Excellent. So here we've just differentiated all of those parts. Excellent. And so we're just going to simplify this. Notice here we've got negative and negative. That is often going to be the case. And so here we're going to have 21,000 e to the negative t over 3. And I'm just going to rewrite this guy here back in original, like with that index form. So here's going to be 7 plus 3e negative t over 3 to the power 2. Are you cool with that?
Yep.
Okay. Now, in the original equation, we know that P is equal to this guy here, right? So what I can do, can you see where this P can be substituted into my differential equation now?
You rearrange it?
Oh, well, we do need to rearrange eventually, but I'm just going to first say, do you see that this guy here is actually inside this equation already?
Yes.
Yeah, so if here it's just 21,000, excellent. And here we've got 7 plus 3e to the power negative t, but squared, so I can just take out one of them. So here, I'm just going to rewrite this. This is equal to p times e to negative t over 3 over 7 plus 3e negative t over 3. Are you cool with that? Is that cool?
Wait, how about you just...
Mm-hmm.
What just happened? Wait, give me a moment.
Yep.
Okay, I see.
You see? Excellent. Okay, cool. Now that I've done that, what I need to do is I need to try and get rid of this whole dude and just replace it with e's and what's it called? I need to replace it with particularly the e to the power negative t over 3 with p's. Now, there's two parts here. First of all, you've got the thing at the bottom and you've got this thing at the top, right?
Yes.
So what I need to do, as you said, is we need to start rearranging this guy over here. So I'm going to do this on the side here. I'm just going to rewrite. Oh, there we go. I have P is equal to 21,000 over 7 plus 3e to the negative t over 3. Okay, let me maybe write this a little bit cleaner because that is a little bit annoying. 7 plus 3e to the negative t over 3. Okay, how might I start rearranging this?
Move the 21,000 over.
Move the 21,000 over. I'm going to recommend the other way. Get rid of denominators most of the time. So when you get rid of denominators, you just move everything from underneath and you move it to the other side. So here I'm just going to rewrite it as p bracket 7 plus 3e negative t over 3 is equal to 21,000. Are you cool with that?
Yep.
Oh, actually, no, you're right. I'm actually going to do 2 steps here because of a really interesting thing that you know. So you said move the 21,000 over, right?
Yeah.
So what are you going to get? What's going to be on the left-hand side if you move the 21,000 over?
P over 21,000.
Is equal to?
1 over 7 plus 3e the power of negative 3. That.
That guy, right?
Yeah.
Now, immediately, hopefully you can start to see, actually, I can sub this into my equation already. Do you see that? It's already here at the bottom. So what I can do is I can go, okay, I've already got this next bit. So I can go, okay, this is equal to P times P over 21,000 times what's left over if I substitute that in.
E to the power of negative t over 3.
Excellent. Are you cool with that?
Yep.
Okay. So from there, we need to start getting to this, get rid of this t, e to the power of negative t over 3. How can I do that?
Rearrange further up there?
Rearrange further. Now, notice here we've got 2 sides both have fractions, right?
Yeah.
So what I can do is I can just flip both sides.
Okay.
It works. So here, I'm just going to flip both sides. So on the, I'm going to swap the 2 sides as well. So on, actually, no, it doesn't matter. On the left-hand side, I'll get 21,000 over p. Are you cool with that?
Yeah.
And that's equal to, what's this equal to on the right-hand side?
7 plus 3e to the power of negative t over 3.
Excellent. Cool. Okay, now that we've got that, I can keep just rearranging stuff and we'll eventually get to e to the power of negative t over 3, right? What's the next thing I need to do?
Minus 7.
Minus 7. So here I'm going to get 21,000 minus 7. Now, when I minus 7 and put it over the fraction, what's going to be? It's not just going to be minus 7. It's going to be minus
7p.
Yep. Excellent. Is equal to 3e negative t over 3. And the final step is to
Divide by 3.
divide by 3. So e negative t over 3 is equal to 21,000 minus 7p over p 3p. Like that. Are you cool with that?
Yeah.
Okay, and then we can substitute this in. So here we can just go, okay, p times p over 21,000 times 21,000 minus 7p over 3p. Are you cool with that?
Yes.
Okay, almost there. Now notice we want to show this equation at the top here. So I'm going to go, okay, great. I just need to start to rearrange stuff. What can we first do? We can...
Cancel out the p's.
cancel out the p, so I can get rid of the p. Now, notice here, I want 1 over 3, 1 minus p over 3,000 times p. So in there, I've already got this p at the front, which is great.
Yep.
So I've got the p which is at the end here, which is
You got
nice.
the 1 over 3.
Where do I get the 1 over 3 from?
The 3p.
The 3p at
The
the bottom. So
remaining
here,
3.
I can just take those out. So here, I'm going to get 1 over 3p, and what am I left with?
Be left with 21,000 minus 7p over 21,000.
Yeah, excellent. So you did that all together. So 21,000 minus 7p over 21,000. And what can we do as a final step? Just...
Simplify?
Well, simplify, yeah. But have a look at how they've written it. We've got the 1 over 3. We've got the p. How have they done here, this step, this middle part here? Have a look at this red circle. Have a look at what we've got in this fraction, this bracket over here.
1 in 3,000.
Huh?
There's 1 minus p over 3,000.
Yeah, it's 1 minus p over 3,000, right? Can you see that I can just divide?
Oh, okay.
You can divide both of the terms by 21,000 and you'll get
Mhm.
1 over 3p, 1 minus p over 3,000. Hey, we got there. Fairly annoying. These questions, if you
Oh
have a
my
look at the
God.
marking criteria, this is worth 2 marks. So this is
Oh,
like,
thank yeah. Okay,
this is
so it's worth the
expected.
effort.
In the HSC exam, like anything that's worth like 2 marks or more, it's like, there's going to be a lot of steps involved. This is worth 2 marks. This is like fairly like
This is
long
only for
points.
2 marks.
2 marks.
Can't imagine what 3 marks and what they make you do.
Okay. Are you cool with this first one?
Yep.
Okay, part 2. Part 2. What is the population today? What do I need to do for this second part?
T equals 0.
Sub t is equal to 0 into which equation?
The first equation,
The
the
first
P
equation, into p.
equation.
So here I'm going to get p is equal to 21,000 over 7 plus 3e to the power 0. What does that become?
Oh. 10 will be
21,000 over
41,000. No. 2,100.
Yeah, because you're dividing by 10, so you get 2,100. Excellent. Okay, part 3. And here I've actually told you what the key word is. Part 3. What does the model predict that the eventual population will be? What's the key word that you notice in this question?
Eventually.
Eventual means what do we need to do?
T equal infinity.
So it's not t equal infinity. Take the limit as t goes to infinity. So similar to when we did when we started looking at differentiation, we said we want to take the limit as t goes to infinity. So here we want to take the limit as t goes to infinity, and we're going to put that into our population. So here, now let's have a look. The population is equal to 21,000 over 7 plus 3e to the negative t. Now, if I take t goes to infinity, what will happen to this e term?
It will disappear.
It will disappear. It will go to 0. So what am I left with? So this will then go to... And do the full working out.
It will eventually goes to 3,000.
You go to 3,000, but if you did the working out, you'd get 21,000 over 7, which is 3,000. So the eventual population will be 3,000. Is that cool?
Yes.
Excellent. Now, part V.
Well, that's it?
Huh?
That's it?
That's it.
Okay, what the hell?
So
The
last
downgrade.
lesson, do you know last lesson when we did this question, the reason why last lesson I did it like step by step was just to show you like how we actually got to this value. But if you're able just to see, okay, e to the negative t goes to 0, if t goes to infinity, then you're good.
Okay.
Yeah? And that's because, just remind me, which direction, so where does so if I'm graphing e to the negative t, where does it start and where does it end? So if I'm going from left to right, where does it start?
Oh, God. It's up from...
So
then
so you can say top left, top right, bottom left, bottom right. Where does it start from?
top left.
Top left, and it goes down towards where?
Bottom.
Bottom, like here,
No, not there. Above the x-axis.
above the x-axis. It goes towards 0, right? And so
Yes.
that what this tells me is as x goes to infinity, or here it's t goes to infinity, e to negative t goes to 0. Exactly that. And that's all you just need to visualize and remember. But yeah. Okay. Part 4. What is the annual percentage rate of growth today? Now, there's a word here that we've looked at before, which makes us...
Annual?
No. What's the keyword that we're going to which tells me which equation I'm going to use?
Percentage rate of growth.
Yeah, what's the keyword?
Today.
No. Oh, actually, today is a keyword because we're substituting. It's going to be like we're talking about t is equal to 0, but there's another word here that tells me which equation I'm going to sub it into.
Rate of growth.
Rate of growth. What does that tell me? I need to substitute this into what equation?
The differential equation.
Yeah, differential equation. Now, in the previous part, we showed that dp on dt is equal to 1 over 3p, 1 minus p over 3,000.
Oh, wow, this is going to be tedious.
Trust me, it's not. Okay.
Oh.
Does this equation have any t's in it?
No.
No. Which is really annoying. Because we wanted to sub in t is equal to 0. But if you have a look at some of the previous parts, we've actually done that. What do we find in one of the previous parts, Khan?
It's the negative 21,000 time e power negative t over 3 times 7, and the whole thing, and then negative 2 is the first thing that we've done.
The first statement that we've done. Okay, cool. So we did this first statement right here. You're talking about this one, right?
Yes.
There's a much easier one.
Or the one above it.
Even easier than that, but be past when we did that. We want to find the rate of growth when at today, right? Which is t is equal to 0. Notice here in this equation, what's the variable that they have this equation in terms of?
P?
P, right?
Yeah.
So what we can do is just find the value of P when t is equal to 0. When t is equal to 0, what's the value of P?
Oh my god.
Yeah?
Oh my... It's 3,000.
What?
Isn't it?
T is equal to 0!
Yes. What? Wait, t equals 0, p is equal 3,000.
I'm just highlighting this form.
Oh my 31.
Can't, don't
2000, 2010, 2100.
Oh, 2000! Oh! Look at that!
Yeah, I just realized this whole thing is 21. Yeah.
Think, Khan, think. So what we can do is, because we have this in terms of P already, it's like this form, hopefully you can see, it's really simple, right? We can just sub in 21,000. So here, 1 over 3 times 2,100 times 1 minus 2,100 over 3,000. Are you cool with that?
Oh my god.
Oh my god. And it's so easy. So here, this is just 700 times... Was that 700? I think it's 700. 700? 700? When did I do this one? 700 times... this should be... What are we left with? This is 1 minus 7 over 10. So that's 3 over 10. 3 over 10, which will give me 21. Is that correct? No. What will that give me? 210. So that's telling me that the annual rate of growth at the beginning is 210 elephants per year.
Okay.
Now, is that what the question's asking me to find?
No.
What are they asking me to find?
Annual.
Annual what?
Percentage rate.
Percentage rate, right? So here, this is not a percentage because percentages, just remember, out of 100, right? So what we need to do as a final step is annual percentage rate of growth. Well, we want to compare this number to another number. What do we want to compare this to? Over. Well, we want to just compare it with how many elephants are at the time when we're measuring this rate of growth. How many elephants are there at the time, at the beginning?
21,000.
21,000. And because we want it as a percentage, we just times it by 100. What's this as a percentage?
Shit. 10%.
10%? Yeah, there we go. There we go. That's how we solve. So this is what this question is telling me is that this population is growing at 10% of its total population. That's what it means. Okay. This is annoying. I'm gonna have a look at a couple of questions. Oh, this one is actually really good. Oh, I wish we had more time. Okay.
Wait, so what happened to Boyd?
His audio doesn't work for some reason, or video doesn't work. So he sent a message on Google Classroom at 7:45. So if you check that.
Okay.
There we go. So that's that. Okay. Now, the two examples that I want to go through from here are actually example 12 and example 14.
12 and 14. I see.
Now, which one do you want to go through? Because we've only got 10 minutes, which makes it really annoying. Oh, okay. Let's have a go through example 14 because this actually applies some of the stuff that we looked at in earlier in this course, earlier in actually before end of last term. So
Okay.
here, the population of foxes on an island is modeled by the logistics equation, this guy here. So this is already telling us it's a logistics equation, it's in this form. Okay, where y is the fraction of the island's carrying capacity reached after t years. At time t, the population of foxes is estimated to be a quarter of the island's carrying capacity. Okay, part 1. Use the substitution y is equal to 1 over 1 minus w to transform the logistics equation to dw on dt is equal to negative w. Now, we want to show this guy here. And what we want to do is we want to use the substitution y is equal to 1 minus w. So what we want to do is we want to replace y with 1 minus w into this into our differential equation to begin with.
Okay.
Now there's a bit of a problem because this equation is dy on dt. We want to get dw on dt. How might we actually get from dy on dt to dw on dt?
Substitution.
Well, yeah, it's a substitution, but we also need to do a what?
Rearrangement of dy and dt.
Yeah, dy on dt. So dy on dt is going to be equal to
Y minus y squared.
No, you don't need to worry about that for now. You know how when we did what's it called? When we did substitution, integration by substitution, right?
Yeah.
So when we wanted to integrate something and change the variable, what did we have to do? So let's say I had like an equation here. So I wanted to integrate some equation dx, and I wanted to integrate it with respect to du. What was the first step we had to do?
Put everything to. Oh, and yeah, differentiate the quite a substitution.
Yep.
And then rearrange the substitution for du on one side and dx on the other side.
Yeah. Now, that's the same here as doing one of the steps that you've actually remembered, hopefully from related rates. So notice here, I've got this equation for dy and dt, right?
Yeah.
What we want to do is we want to figure out a way to relate dy and dt and dw on dt.
Okay.
So
Yes.
how do I get dy and dt is equal to some form of something related to dw on dt? What do I need to multiply this by to make it work?
God.
And maybe I'll rearrange it in a different order. What do I need to do? So
do off. God, fuck.
D.
Oh my god.
Have a look at the left
dy over dw.
dy over dw. And so
God.
here we've got this guy. This works out fine. Because if you have a look, we can get a value for dy and dw. We can actually differentiate this equation here.
Yes.
And then that will give us dw on dt. So here, let's actually work about all of these parts. Now, let's start off with the left-hand side. Now, dy and dt, we want to use that substitution. So what I'm going to do is I'm just going to replace everywhere I see y in this original equation with what my substitution is. So let's actually replace that. What does this become if I use this substitution?
Why? Wait. You differentiate it.
We don't need to differentiate it yet. We just rearrange because this is that original equation here, but we're substituting that 1 minus w into here.
Time negative w.
So this is 1 over 1 minus w times
Negative w.
negative w. Is it negative w? Negative w.
It sets the thing right there. The logistic equation to dw over dt equal negative w.
Oh, we want to show that this is the case. We don't want to actually... We need to show that. So what I'm doing here... So just to show you... So do you notice that we start off with this equation? That's what they've given me the information for.
Yes.
At the top. They tell me that I need to use this substitution here.
Okay.
So what I'm doing at the first part is I go, okay, I've got this equation here. I need to substitute 1 minus w in to wherever I see y. So that's why I've got this guy here.
But that's not rates. It's just normal.
It's just normal, but we're using substitution here.
Okay.
And I'll show you, like, hopefully, but at the end of this, you'll be like, oh, okay, I can see how this works. So here, notice here, I'm just substituting this 1 minus w, 1 over 1 minus w into this guy here. Are you cool with that?
Yes.
Let's just rearrange this. So this becomes 1 over 1 minus w times, what will this fraction become?
Wait, why is it 1 minus 1 minus 1 over 1 over?
Because that's the bracket part of my original differential equation at the top. You see here, it's y times 1 minus w, y.
Oh, so you just have to. Okay.
What does the bracket become?
The bracket become 1 over 1. Negative w over that, over the whole thing.
Yeah. So here I've got negative w over 1 minus w squared. Are you cool with that?
Yes.
Okay. On this side, we can figure out what dy and dw is. So dy and dw, what do I need to do?
Divided up. Differentiator.
Yeah, differentiate this guy here, right? So
Oh
here,
my god! Okay, I just realized what you've done.
so that's that guy. So what do I get for dy and dw?
Negative
Negative.
times 1 minus. Wait, times negative 1?
It's negative. So it's going to be... So what are you doing first? You differentiate the inside. What do I get when I differentiate the inside?
Negative 1.
Negative 1 times. Differentiate the outside part now.
Negative 1.
Times.
The whole thing.
To the power.
Negative 2.
So this becomes
Okay.
1 minus w to the power negative 2, right? That's 1 over 1 minus w squared. Cool with that?
Yep.
Okay. What I can do is now I can substitute these two things back into the original equation. So the original equation will just become negative w over 1 minus w squared is equal to 1 minus w squared times dw on dt. You see that?
Yes.
And what can I do from here that will get me my answer?
Start solving. Oh, wait, yeah.
Solving? How can I solve both sides? What can I firstly do?
Move dw over dt to one side.
Oh wait, we don't need to worry about that now. Have a look at what we want to show. We want to transform
dw.
the logistic equation into this guy.
Yes.
What do we need to do?
Cancel out the denominator.
And so therefore, dw on dt is equal to...
Negative w.
That's it.
Okay.
So for this one, you actually need to use some chain stuff to actually get you there. Okay, are you cool with that?
Yes.
Okay. Part 2. Using the solutions of dw on dt is equal to negative w, find the solutions to the logistics equation for y satisfying the initial conditions. So this is where what you said is correct. Now we want to solve. So here I've got dw on dt is equal to negative w. What we want to do is we want to solve it. And this is where your differential equation stuff will be required. So what do we need to do here? And what you said earlier is correct now.
Differentiate substitution. Differentiate the substitution.
No, we don't need to do that.
What did I say at the start?
This guy here, how would you normally solve this now?
Differentiate substitution and rearrange it.
What did we do earlier in this topic?
Rearranging equation.
Rearrange the equation. So what did we have to do? We wanted to move all of our...
So all the y on one side and x on one side.
Yeah. But this case, it's not going to be y and x. It's going to be...
Y and w. Y and t?
That's a y?
Oh, shit. Okay. Oh, okay, so using the solution of w. Okay.
Yeah, we're going to use this. We're going to use this guy. And we're going to start solving. So we're going to move all the w's to one side and all the t's to one side. Are you cool with that?
Yes.
So let me do that. So I'm going to move the W to the other side. So I get dW on dW on W, right? Is equal to... Oh, actually, I'll move the negative sign too. Negative dW. Negative W is equal to what?
dt.
dt, right?
Yep.
So then what can I do from here?
Okay.
Integrate both sides. Now,
Yeah.
on the left-hand side, what am I going to get?
There you got negative ln w.
Is equal to...
1. Oh, no, x. Oh, no, t.
And what do we also need to include?
Plus c.
Excellent. Now, at this point, we can actually solve the initial condition. What's the initial condition from this question?
T equals 0.
Solve.
And it's
T equals 0.
estimate.
It's estimated that what is happening? The population of foxes is estimated to be?
1/4.
1/4. Now, the population, what's the letter that represents the population?
P.
In this scenario, what is it?
Oh, in this scenario. Okay.
It's not P.
W?
Have a look.
W?
Read the question. It's not W.
Y.
Y. So here it's telling me Y is equal to, what's the value for Y?
It's the fraction.
Mm-hmm.
So it's 1/4.
1 over
Y.
4. Excellent. Y is equal to 1 over 4. Now, if you have a look at the equation that we have in the line before, we've got T, which is great, but do we have Y?
No, we don't.
No. We have W, right?
Yep.
So what we want to do is we want to figure out what the value of W is going to be. How can I find the value of W based off of Y? Look at the big red circle.
The substitution.
Yeah, so what's W going to be equal to then? If Y is equal to 1 over 4, then W is going to need to be equal to...
5.
What?
Oh, wait.
Other direction. Let me give you a hint, it's a negative number.
Oh, no. Oh, no. Oh, no.
So you've identified that
Wait,
1 minus
I-
W is equal to 4, right?
Maybe I can do this.
I'm just going to slowly do this until...
5! Wait, wouldn't it be 5? What? I can't do this.
Can't? This is what Y is equal to, right? Y is equal to 1 over
Yeah,
1 minus W, right?
yes.
And we said that Y is equal to 1/4.
Yes.
From here, what you want to do is then go, okay, well then 1 minus W is equal to 4.
No, okay, I see. And you minus a 1 and it becomes a -3.
Oh, Khan, for the love of God. Please. Okay, so we can substitute these values in. So what am I going to get on the left-hand side? Negative ln?
4. Oh, negative.
Is equal to?
Wait, why? Oh yeah, it's absolute value. Okay, I see. T plus E.
T plus C? What's T?
Time?
What's
Oh,
T?
T equals 0.
So therefore, C is equal to negative ln3. And so in my equation, it's going to become negative lnw is equal to T minus ln3. Oh, jeepers. Breathe.
Wait, why is it negative C? Wait, hold on. Oh, that's just a dot. Okay, I thought it was
Okay.
a negative.
Now from here you can continue to solve this and actually rearrange this equation, and so you would end up getting, I believe, W is equal to W is equal to 3e to negative t, which means that Y would be equal to 1 over 1 minus 3e to negative t, and you would get that solution if you kept going. Unfortunately, we've actually gone over time, so I will leave this. I'll send you guys a few questions on the Google Classroom to have a look at. at your own time. But yes, that is it for today's lesson, Khan.
Oh, no.
Next lesson, we're going to go through sketching some slope curves. So please, for the love of God, rock up on time. Jeez.
I was 5 minutes late.
More than 5 minutes late. How dare you? How dare you, Khan? Okay, but that is it for today's lesson. I will try and post this on onto Google Classroom. It's a little preview video. Yeah, stop.